A gate family is universal or functionally complete when it can build every Boolean function. We already know that NOT, AND, and OR can describe any Boolean expression. So the proof strategy is practical. Use one gate family to reconstruct those three operations. NAND starts as AND and then inverts its output. NOR starts as OR and then inverts its output. In both symbols, the small circle at the output is the inversion bubble. It is an electrical operation, not decoration. The first construction is an inverter. Connect both inputs of a NAND gate to the same signal A. The gate computes the complement of A and A. Since A and A equals A, the output is A prime. The same idea works with NOR. A or A also equals A, and NOR complements it. In the schematics, the junction dot shows that both input pins belong to the same electrical node. One NAND or one NOR can therefore reproduce NOT. Now recover each family's base operation. A first NAND produces the complement of A and B. Feed that result into both inputs of a second NAND, which acts as an inverter. Double inversion leaves A and B. Two NAND gates therefore reproduce AND. The NOR construction is parallel. A first NOR produces the complement of A or B, and a tied input NOR inverts that result again. The output is A or B. With NOT plus the recovered operation, De Morgan's laws can supply the remaining operation. Let us implement F equals AB plus C using NAND gates only. Read the circuit node by node. N1 is NAND of A and B, so N1 equals the complement of AB. N2 has both inputs tied to C, so it acts as an inverter and produces C prime. The final NAND receives N1 and N2. Its output is the complement of their product. Substitute the two-node equations. The final result is the complement of AB prime times C prime. By De Morgan's law, that equals AB plus C. Three NAND gates implement the complete function with no separate NOT, AND, or OR symbols. A schematic is not finished until its behavior is checked. The table compares the direct expression, AB plus C, with the three internal NAND nodes. For each of the 8 input combinations, compute AB and copy C. Then N1 is the complement of AB, N2 is the complement of C, and the final output is NAND of those two nodes. Every final value matches the direct expression. Notice the last two rows. When A and B are both 1, AB forces F to 1 regardless of C. This complete row-by-row agreement is the strongest QA for the circuit. The universal gate workflow has 3 reusable moves. Tie a gate's inputs together to create NOT. Invert a NAND or NOR result again to recover AND or OR. Then use De Morgan's law to connect complete terms while staying inside one gate family. Universal gates matter because real designs can be standardized around a small library of repeated cells. Next, we will combine gates into larger functional blocks, beginning with decoders and encoders.